Coming up on Destination Tomorrow, we'll discover that playing video games might help people with Attention Deficit Hyperactivity Disorder control their behavior. We'll also see how new technologies are making air travel safer and more efficient. And we'll meet an engineer who developed a wingless vehicle that revolutionized spacecraft designs. All this and more next on Destination Tomorrow.
Hello everyone, I'm Steele McGonigal.
And I'm Kara O'Brien. Welcome to Destination Tomorrow.
This program will uncover how past, present, and future research is creating today's knowledge to answer the questions and solve the challenges of tomorrow.
The International Space Station orbits the Earth every 90 minutes and will provide an orbital laboratory in a reduced gravity environment for long-term research. This microgravity environment gives researchers an opportunity to study the fundamental states of matter, solids, liquids, and gases, and the forces that affect them.
A unique facility at NASA Glenn is able to conduct microgravity research here on Earth. NASA researchers can study how the lack of gravity will affect the experiments before they are brought into space. Jennifer Pulley takes us inside NASA Glenn's 2.2-second drop tower.
By now, you've all seen astronauts and objects floating around inside an orbiting spacecraft, seemingly free of Earth's gravitational field. But these images are misleading. In fact, these objects are actually not floating, but in a state of continuous freefall. Any object in freefall experiences microgravity, or weightlessness, which occurs when the object falls towards the Earth. Before NASA researchers send experiments on board shuttle missions or to the International Space Station, they often test them here on Earth. But how do you replicate microgravity here on Earth? NASA Glenn has been conducting microgravity experiments since the 1960s in drop towers like this. These facilities rely on free fall of the experiment to produce a microgravity environment. Here, NASA can test experiments in a reduced gravity environment, similar to orbiting in space.
The 2.2-second drop tower is one of two microgravity facilities here at the Glenn Research Center. This facility is just under 80 feet tall. We can drop experiments in this facility weighing up to 350 pounds. They'll reach a terminal velocity of almost 50 miles per hour just before they hit the airbag at the bottom of the tower. We create microgravity for 2.2 seconds here.
You said microgravity. Do you mean weightlessness?
Yes, that's exactly right. Microgravity is weightlessness. Astronauts experience that in orbit all the time. But we need to create that down here on the Earth, and we can do that here in the 2.2-second drop tower.
This is how a drop tower experiment works. Researchers place their experiments inside an aluminum frame, also called a rig. Experiment rigs are then placed inside a drag shield, but are not attached to it. Once assembled, the experiment package is lifted to the top of the tower, then released. When the experiment is dropped, it experiences microgravity, or zero-G, for 2.2 seconds. The drag shield protects the experiment from aerodynamic drag during the drop, which allows the experiment rig to fall freely a distance of 7.5 inches. The experiment experiences weightlessness, similar to what would be expected in space.
Here in the drop tower, what happens is the experiment falls to the tower inside the drag shield. The drag shield is being slowed down by the aerodynamic drag as it approaches 50 miles an hour as it nears the bottom of the tower. The experiment inside, however, is falling through 7.5 inches inside the drag shield and is unaware of the aerodynamic drag that's occurring around it. There's three kinds of microgravity experiments we perform. Most of our work is centered on combustion. All the experiments are basically the same internally. There's a power system, there's a computer system on board to control the experiment as it falls through the tower. There's a diagnostic system on board which takes the imaging or the pressure or temperature data from the experiment as it falls. And then there's the experiment itself, the thing that's actually burning or the liquid that's moving around inside the experiment. And we get all this ready, raise the experiment to the top of the tower that we have now, and we close it up, package it up, do a countdown.
Stand by for go. 3, 2, 1.
And as the experiment falls through the tower, it's in microgravity. That's when the experiment runs.
Why do we conduct microgravity experiments here on Earth when we can easily conduct them in space?
Well, actually, to conduct them in space is quite expensive. The numbers I've heard is about $10,000 per pound just to lift the experiment into space. Not to mention the cost of having the astronaut operate the experiment while it's up there. Here in the drop tower, it's quite a bit less expensive to do that. And if we make a mistake, we can go back and run the experiment again quite rapidly. Our researchers set up the parameters for the experiments that do go up to space, right here in the drop tower.
So how do the combustion experiments that you conduct here at this facility in microgravity affect me, the general public?
Well, the whole idea here is to understand combustion at the fundamental level. Once we understand that, we can go out and make cleaner burning engines, cleaner burning power plants, which means less pollution in the air. So we're less fuel dependent and we have a cleaner environment.
The 2.2-second drop tower was originally built in 1948 to house a distillation tower for making jet fuel. In the mid-1960s, the need to perform reduced gravity research in support of the space program saved the facility from being torn down. Now, coming up, we'll see how playing video games can help people overcome attention deficit hyperactivity disorder. But first, did you know NASA uses a specially adapted plane nicknamed the Vomit Comet that creates microgravity here on Earth? When the plane reaches the top of a parabolic trajectory, the occupants temporarily become weightless, experiencing what it is like to fly in space.
It seems like video games are just about everywhere. People have them in their homes, on their computers, and even small handheld versions. NASA uses simulators, which are similar to video games, to train and help pilots stay focused while flying a plane. Derived from this research, NASA researchers have incorporated the use of video games to help treat patients with attention deficit hyperactivity disorder. Linda Beth Bureau explains.
Have you ever met someone with attention deficit hyperactivity disorder, or ADHD? Chances are that you have. It is estimated that as many as 6% of all Americans suffer from this problem. Common symptoms of ADHD can include poor attention span, impulsive behavior, and in some cases, hyperactivity. Currently, drug treatment is the most widely used approach to control the unwanted behavior associated with ADHD.
But would you believe that playing video games might help people with ADHD control their behavior? Researchers at NASA Langley Research Center and Eastern Virginia Medical School have been conducting research which shows that the use of a specially adapted video game controller in conjunction with something called biofeedback may drastically change the way we treat ADHD.
We came up with this idea for a way to treat ADHD in children with our work in flight simulators, where we were interested in pilots' attentiveness and how to improve that. We connected their brainwaves to the flight simulators so that it affected how much control they had over the flight simulator. We decided that this might have some usefulness in brainwave biofeedback training, and we substituted video games for the flight simulator, and that brought the element of motivation, the entertainment value, into biofeedback training.
Biofeedback is a treatment technique that teaches patients to train and control normally involuntary body functions, like brainwaves, by using displays of signals from their own bodies. With the aid of a biofeedback machine, patients with ADHD can learn to train the brainwaves that are associated with focusing. Patients train these brainwaves by increasing the strength of high-frequency beta waves and decreasing the strength of low-frequency theta waves. Practicing these brainwave changes has been shown to lead to an improved ability to pay attention. These brainwaves can be trained much like an athlete trains his muscles. For example, when a pitcher throws a ball towards home plate, if he is off the mark, then he must adjust his delivery the next time he throws the ball. Biofeedback training works similarly. If a patient's brainwaves are not on target, then the patient must adjust his brainwaves to meet the desired goal. So, just as the pitcher uses his muscles to adjust his delivery, the patient uses his mind to adjust his brainwaves.
Video games offers the element of motivation. They make the training, biofeedback training, entertaining for children. Biofeedback training typically is just showing children displays of their brainwaves and asking them to control that. What we've done is embedded that in an entertaining, enjoyable activity. This technology works by connecting a child's brainwaves to a video game controller.
In the NASA EVMS study, several off-the-shelf video games were linked to the biofeedback signal from the patient's brainwaves through the handheld controller that guides the game's action. When the game was activated, the patient's brainwaves actually became a part of the game. It works like this. While a patient is playing a car racing game, for example, the sensors pick up high-frequency beta waves and low-frequency theta waves from the player's brain. If the biofeedback machine reads a higher percentage of theta waves, it sends a signal to the controller which lowers the top speed that the player's car can reach. To increase his top speed, the player must increase his percentage of beta waves. The player learns through trial and error to produce more beta waves and not limit his car's top speed. With enough training, changes in the patient's brain become automatic and can lead to improved attention and behavior all the time.
I would like to see this available to people to be able to bring into their home and enjoy the benefits of biofeedback training through entertaining activities.
Home versions of this technology are currently being developed that would incorporate sensors embedded into a helmet to measure players' brainwaves. If this technique continues to prove to be effective, one day kids may actually have a good excuse to play video games.
We've all seen the space shuttle taking off, but most of us take its design for granted today. It wasn't too many years ago that this unusual design shape was considered impractical. That was until a resourceful engineer from NASA named Dale Reed began working on design shapes called lifting bodies, which would change the shape of reusable spacecraft. The lifting body concept evolved in the late 1950s as researchers considered alternatives to the simple ballistic design of space capsules. Many felt that astronauts should have a more sophisticated vehicle that they could fly back and land on Earth from space. The lifting body idea was unusual because the vehicle didn't have any wings. The shape of its body alone had sufficient lift to fly. Despite favorable research on lifting bodies, there was little support for a flight program at NASA headquarters. Engineer Dale Reed decided that a flight demonstration was needed before wingless aircraft could be taken seriously. So, in February 1962, he built a model lifting body and launched it from a radio-controlled mothership in his backyard. While Dale flew the model, his wife took home movies of these flights, which helped Reed convince his boss to give the go-ahead for the construction of a full-scale version. But they would have to build it without funding support from NASA headquarters.
There was very little confidence among NASA headquarters planners of spacecraft missions in the lifting body concept. It was strictly a theory and an idea that a few technical people had. We flight test people felt that if we were to fly one of these and demonstrate that they can fly, then they would be the lifting body would be considered for future designs for future spacecraft.
NASA craftsmen and engineers took on the task and began building this new vehicle that they dubbed the M2F1. It was built with a tubular steel interior frame and a mahogany plywood shell.
We did this on an informal basis. I was allowed to select my team of engineers and technicians that had experience in building home-built airplanes. And we proceeded with the design and construction of the vehicle in that fashion.
Once the vehicle was done, Reed and other engineers towed the M2F1 across the desert runway with a souped-up Pontiac convertible. On April 5, 1963, pilot Milt Thompson lifted the M2F1's nose off the ground for the first time, proving the lifting body concept. Later tests were done with a NASA C-47 that lifted the M2F1 to about 12,000 feet and released it. The lifting body dove toward the ground at 150 miles per hour, but the landing was smooth and the lifting body program was on its way.
That was probably the most exciting thing in my career, with Milt Thompson being released at 12,000 feet, doing a successful flare out of a very steep approach and coming very softly on the lake bed. I feel very proud of the fact that we accomplished a very major milestone in history by demonstrating an airplane that can fly without wings and that can be applied to exciting designs of the future, especially in the spacecraft field.
More than 400 ground tows and over 100 aircraft tow flights were carried out on the M2F1. The lifting body research was used heavily in the design of the space shuttle and is still being used today to design new vehicles like the X-38. The lifting body program has proven to be one of the most valuable programs in NASA history.
During the course of the original lifting body program, 6 different lifting body shapes were flown a total of 230 times, eventually reaching an altitude of 90,000 feet and a speed of Mach 1.86. Coming up, we'll see how NASA researchers are developing new technologies that will make flying safer and more efficient. But first, Did you know that the M2F1 was very inexpensive to build? The budget for the project was only about $30,000. In comparison, it is more expensive to operate an F-15 fighter for 5 hours.
Have you ever been delayed at the airport? Chances are that you have. Most of us assume that flight delays are just an unfortunate part of traveling. Well, researchers at NASA are working on a program called Aviation Systems Capacity that just may make flight delays a thing of the past. Our own Jennifer Cortez takes us to NASA Ames to find out more.
Have you ever been in this situation? Long lines at the airport, your flight's been delayed again. Sitting on the runway waiting to take off, or circling the airport waiting to land. Unfortunately, it seems as if delays and cancellations are becoming a routine part of travel. Over the next 20 years, the demand for air travel is expected to double, which could make these delay problems much more frequent. In fact, by the year 2012, there will be over 1 billion passengers traveling on domestic flights annually. But is there anything that can be done about these delays? Well, researchers at NASA are working on something called Aviation Systems Capacity, which may someday make flight delays a thing of the past.
There are many factors that affect delays at major airports throughout the country. The major one is that there is just an exponential growth in the amount of traffic in the air traffic system. And unfortunately, we are just using the old air traffic control system that has been around for years.
To better understand why some airport delays happen, think about your own rush hour traffic. As long as everyone is going the same speed, traffic moves smoothly. But if weather is bad or a few cars or trucks slow down, then huge backups can happen. That same basic thing is happening in the airport environment. Air traffic may be running smoothly, but if one plane is delayed because of weather, backups start to occur. Unfortunately, if planes are late leaving one airport, then those same planes arrive late at other airports, causing further delays. NASA's goal is to safely increase the capacity and productivity of national airspace by developing revolutionary operation systems and vehicles.
Now, NASA has been working on 3 projects, and these 3 projects are aimed at trying to develop the technologies that will increase the capacity on the national level. First 2 projects are the Advanced Air Transportation Technologies Project and the Terminal Area Productivity Project. Those 2 combined are looking at technologies that will help reduce the workload of both pilots and controllers at major airports. In addition to that, NASA is developing an aircraft that will be able to fly in and out of major airports without needing the runways.
Frank, I know that you want to get aircraft in and out of airports faster. How are you going to do that?
Well, Jen, since 70% of all delays in and out of major airports are caused by weather, NASA is working on technology that will allow traffic to safely come in and out of these major airports, even under bad weather. And so in order to do that, NASA is working on a technology called Airborne Information for Lateral Spacing, which will provide the pilot the ability to see other traffic even during the bad weather times so that they can safely come in and out of these airports. So based on doing that, we would be able to increase capacity at major airports. And the third element in the capacity program is the short-haul civil tilt-rotor project.
The civil tilt-rotor aircraft offers a unique opportunity to alleviate runway congestion at the busiest airports. With the advantage of vertical takeoffs and vertical landing, tilt rotors don't rely on conventional runways and can bypass ground and air congestion, which reduces door-to-door trip times for passengers. With trips of less than 500 miles, tilt rotors will reduce the amount of fixed-wing flights, which would free up runway space for larger aircraft.
The benefits of the tilt rotor are that you can take off and land vertically, and then you can fly like an airplane. So it can fly twice as far and fast as a helicopter, and at its destination the reverse occurs and it lands like a helicopter. And the big advantage is you don't need runways, and also you don't even need airports. You can fly to small landing areas that we call vertiports, and these could be located much closer to where you're going or where you're coming from, and therefore you avoid all of the congestion on the ground and at the airport and in the air. That's why I believe the tilt rotor will revolutionize air travel.
Some initial milestones for the Aviation Systems Capacity program have already been accomplished and are currently being tested for future use in airports.
We've all seen helicopters flying around, but do you know how they work? For some answers, we turn to Johnny Alonso.
For 60 years, the helicopter has been one of the most versatile types of transportation around. They have the ability to fly forward, backwards, sideways, rise and descend vertically, and hover motionless in the air. Helicopters have been credited with saving over 3 million lives by transporting critically wounded people from accidents and war zones. They're also used for things like helping the police fight crime, fighting forest fires, and simple tasks like checking our roadway conditions. But have you ever wondered how helicopters fly? For some answers, I spoke with NASA Langley researcher Mike Watts at the Coast Guard Air Station, Elizabeth City.
Johnny, to really understand how a helicopter flies, first let's go back to a fixed-wing world, a regular airplane, the kind with wings and an engine. Now, a fixed wing has an engine, a jet, or a propeller to push you through the air, and that moves air over the wings, which provides lift that keeps it in the air.
I see.
And obviously from this helicopter, you can see we don't have normal wings, and we don't have a jet or a propeller on it to push you forward through the air. But what you do have is the main rotor blades. You can notice that these are shaped a lot like wings for a fixed wing. The way you get them moving through the air is these rotate around in a circle, and that moves them through the air. They're shaped just like a wing, so that provides a lift force that lifts the helicopter off the ground.
Cool. So you've tapped in on how a helicopter lifts off the ground. Can you explain to me how you control the altitude?
Sure. The way you control the altitude is by generating more lift or more upward force. And the way you do that is you pitch the rotor blade to a higher angle in relation to the wind. That generates more lift, and that lifts it off the ground. Okay. To go down, you just reduce the angle of the blades that generates less lift, and the gravity settles you down into the ground.
So this is the main rotor. What is this?
This is called a tail rotor.
Tail rotor.
As you can see, it looks like a main rotor or a propeller on its side. When you turn the main rotor blades, the body of the helicopter wants to go against the rotation. So if the blades are turning this way, the body wants to go this way. Well, to keep straight, you have to provide something to counter that turn, that force pushing it sideways. So we provide a force that keeps it straight. And that's what the tail rotor provides.
Wow.
If you want to go to the left, you provide more force, and it goes this way. If you want to go to the right, you provide less force, and the torque turns it this way.
So Mike, you briefly explained to us how you keep the helicopter straight. How do you make it go forward?
Well, you make it go forward by providing a force to push it forward. Just like in a regular airplane that has a propeller, the propeller is providing a force to push the airplane forward. We need to provide that somewhere. If you think of the main rotor as a disc in the air, and it's got a force going through the center of it, that's what we talked about as a thrust, that holds it in the air. If you tilt it forward a little bit, it's going to pull the helicopter forward. If you tilt it back, it's going to pull the helicopter back. If you want to go sideways, you just tilt it to the side, and it pulls you sideways like that. And so you have the force pulling you backwards, forwards, and sideways.
Sure.
And if you actually take that disc and turn it all the way on its side, it's like a propeller. It's pulling you all the way forwards. And there's a concept being looked at by the Marines now called the V-22 tilt rotor. And that is to turn the rotors on their sides and make them propellers. You get the benefits of going farther and faster for a fixed wing or a regular airplane, and you can take off and land vertically, just like a helicopter.
That's all there is to it.
That's all there is to it.
That's all there is to it. Mike, thanks for coming out and showing us everything about helicopters.
My pleasure, my pleasure.
You got the keys, man?
Oh yeah, let's go fire it up.
Come on, let's do it.
All right, let's go.
An alarm? Let's go. So that's how it works. We'd like to thank the U.S. Coast Guard for letting us use their facilities here in Elizabeth City. So we're taking off now. Let's go to my house. Where are we going to park?
Thanks for joining us on this edition of Destination Tomorrow. I'm Steele McGonigal.
And I'm Kara O'Brien. And for all of us here at NASA, we'll see you next time.